Okay. Some of this you've seen before. A lot of this is just tying two other chapters we've covered together. That's kind of how it's going to be from here on out. So we covered the first 6 chapters, and now we're on the second half. And the second half of the book really should tie together the random junk we did in the first 6 chapters. Like in chapter 1 when we were talking about cussing, and then in chapter 5 when we were talking about how to pick a sample. Now finally, cussing and sample should be in the same thought of frame of mind. And you're like, I don't understand how, but eventually all the things and stats tie together, thankfully. Okay, so today we're going to talk about sampling distributions, which is what I was hoping you were going to learn the other day from that point activity, but I sent you the teacher directions instead of the student directions, because that's what happens when you're sick. You do dumb things, so it's okay. Sampling distributions can give us key insight, and if we're trying to make an inference about a population, we're going to need to make a sampling distribution. And you're like, what is that? Well, duh, we need to discuss that. We've actually already talked about these words. They're back from chapter 1. It's just been a long time. So a parameter and a statistic, and how are they different? P is for parameter, yes, but P is also for population. Statistic goes with sample. So P, parameter, population. S, statistic, sample. So they're easy to keep separating. What's the difference between a population and a sample? Okay, sample is a small subsection of the whole. So an example using our class would be a sample taken within our class. Just table 1. If we did just one table, or we did just girls, that's a sample of our AP Stats population. Okay, from this point forward, we haven't really stressed the notation until now, but starting now, we've actually got to recognize this Greek notation. So it says it below, but I'm going to write it here as well, just because I don't know, writing things helps me. Mu is for the mean. Yes, you need to know it's called mu when you talk to me, just so you don't sound silly. Rho is for the proportion. When I think of a proportion, I think of a fraction. You've been doing proportions for forever. Like if they say 5 out of 6 dentists recommend whatever, and then you figure out that percentage, that's a proportion. Duh. Sigma, you already knew that was for standard deviation. And then N is for our size. For instance, our size of our population, if we're doing AP Stats, is the 13 of you. Well, I guess we're counting me 14. And the exact table underneath says this exact same thing. I just like writing things. It makes me learn. So we still talk about the same 4 things if we talk about a sample. But sadly, since a sample is different than a population, we have to use 4 different letters. So yes, this is still the mean. But instead of mu, we call it X bar. Yes, this is still the proportion. But instead of P, we seriously call it P hat. So that weirdo symbol over the P looks like an upside down V. We call that P hat. S is for standard deviation, which we've actually seen that S before. And if you can tell me where, I would probably find something for you.
Oh, is it from that box thingy?
Yes.
With the graph, and it had like the 2 columns.
The linear regression, and someone at that point asked me if that was the standard deviation, and it was. Okay, later on I'll find y'all something. That was good. Okay, and then N is for size. So, like if we're doing just table 1, it would be 5. So we still need to know how to identify the mean, the proportion, the standard deviation, and the size for a parameter, which deals with the population, or for a sample, and the statistic is the term that goes with sample. Okay, they explain exactly what we just wrote in that table. Again, I know this sounds stupid, but X with a line on top is seriously called X bar. And P with a hat on top is seriously called P hat. Now you're like, Ms. Compton, why do I need to know mu is for population and X bar is for sample? Because on multiple choice questions, they might not specify in the question, this is dealing with a population, this is dealing with a sample. Instead, they're just going to use one of those two letters and expect you to know, oh, because they use mu, this is dealing with a population. Oh, because they use p hat, this must be dealing with a sample. So sadly, you do need to know which 4 letters go with population and which 4 letters go with sample. Okay, so after the table, it tells you kind of something you already know, which is that while p is for parameter, and so it's a number we would calculate using the population, it's normally not feasible because we can't examine the entire population because you and I both know it's going to take too long, it's too costly, even the census fails us. So we might leave people out, etc. So instead of doing a population and calculating the parameter, we find a statistic by using some sample data. Now our goal in statistics is to have such a good sample, which we spent a lot of time on in Chapter 5, how to take a good sample. We want to have such a good sample that it is representative of the population. So if we find out 85% of you hate broccoli, and y'all are supposed to be a good sample for the school, then we should be able to say, well, 85% of the people at school hate broccoli as well. Theoretically, that's what's supposed to happen. But if we don't take a good sample, that's not possible. Yes, dear.
So the P that's under population parameter, like for populations,
it's called row. Yeah, notice how it's written kind of sideways, like italicized. Yeah, I might want to add. You might want to add like a little, make it like a cursive P or something so it stands out. Thank you for pointing that out, Jackson. God bless you. God bless you. Okay, so we do have an exercise which sadly involves very few numbers, but whatever. We need to. Yes, dear.
I was gonna say the P hat looks the same as the hat.
They do.
It's still a
It's. I just do normal P with a hat. I actually do more of a cursive P when it's row, and do P with a hat when it's hat. Thank y'all for being very specific. I appreciate that. Okay. We have 2 things we need to identify: the population, the parameter. For A, the parameter. We need to identify the sample and the statistic. Okay, Alex, you're a good reader. Read A.
The Gallup poll asked a random sample of 550 U.S. adults whether or not they believe in ghosts. Other respondents, 160, said yes.
Okay, so our population is who? Yeah, I'm putting U.S. adults. I do. I didn't like that either, but I just decided not to question any further. I assumed it was 18 plus, and then I was like, well, why are we only, I don't know. I felt like that should have been specified as well, but it is okay. Okay, the parameter is the number we would like to figure out for the population. So what are we trying to learn? What is our question? Okay, so that's exactly what I'm going to put. Do people believe in ghosts? Because we would like a percentage, like 80% of people believe in ghosts. Do people believe in ghosts? That's what we would like to learn. Okay, but clearly we couldn't poll and people would not respond to this question. So instead, the Gallup poll took a sample. What should I put as their sample? Okay, so I'm going to put 515 U.S. adults. And I'm going to be even more specific. Polled by Gallup. And I know you're like, this Tom thing, you're being redundant, and I get I am, especially since y'all understand all this, but as we've decided in the past, the more you can show from the stem of the question, the more it shows you actually read the question, the better it improves your score. Seems stupid, but it is important to reference whatever it asked. Okay, so the statistic, what numbers can we actually calculate? That's exactly what we should do. 160 divided by 515, you get 0.31. And so what does that 0.31 tell us? Okay, so it's 31% of the U.S. adults polled by Gallup believe in ghosts. And again, as always, and this seems stupid, I know you're like, Miss Plum, I think I could have handled all this without you, which is why I thought you could, but it's okay. Our goal is to then say, well, what does that sample represent of the entire population? So can we now say 31% of all U.S. adults believe in ghosts? So that's our goal. Okay, are there any questions on A? And we're going to do the exact same thing with B, so we still want to know the population, the parameter, the sample, and the statistic. Now, while I haven't seen a ghost question before, I have seen a free response similar to B. I don't know why, but, well, I do know why, because this is something that people investigate all the time. But a question involving how much we fill up a container, especially a product that people are buying, it tends to be a good free response question, because you end up asking, like, was this a fair product?
Did you hear about Arizona TV reach all across the store?
Yes, I did, so I did find it very ironic.
Because they've done urine, so
Yeah.
I'm pretty sure that was urine.
they're using urine as a tea. Yeah.
Yeah, no, I saw it on a fake news website.
I don't unlike
I don't know. We'll Google it.
I promise it's not true.
We'll Google it in a few minutes. Let's deal with this first, but then we'll Google it. Okay, so here is a different reason to be mad at them besides what their actual product is. So if it bothers you, change it to whatever.
I was eating my chips.
Read B.
On Tuesday, the bottle of Arizona iced tea filled in a plant was supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random for the production. These bottles contain an average of 19.6 ounces of iced tea.
Okay, so why are we already mad?
Because the urine. Okay, sorry.
Well,
continue.
because of the
0.4 ounces of urine.
yeah, the 0.4 ounces of liquid that I thought I paid for. Okay, so let's just one step at a time. Forget the urine. Move on. I swear we'll Google it at the end of class.
You're in trouble for that.
Yeah, that was good, Cody. Okay, who is our population? Oh my goodness.
The bottles of Arizona iced tea.
Yeah, so I put all bottles.
I love the dark green. I love the dark green.
Should we be more specific than this? Why are you going
Oh, I
dark?
thought like you meant for it to go black.
No.
Okay.
Why should we be more? Okay. Iced tea bottles. Should we say in a plant? I'm not going to.
I guess we should.
I thought about putting in the word unopened in case someone was being facetious and they're like, well, I've already drank out of this. So we're talking about ones that have not been opened, but maybe that was implied. Maybe I'm being too realistic. One would think, but people overthink life all the time. Okay, so what are we trying to figure out? What's the parameter? Okay, so our bottles filled to 20 ounces, and to please Cody, I'm going to put a fluids. We would like to know, did they all reach that mark? I'm buying a 20 ounce whatever. Does it actually hit the 20 ounce mark?
20 ounces?
Sometimes not.
Sometimes not, sometimes yes, so now we got to deal with it. Okay, as for our sample, what is our sample?
50 bottles.
50 bottles. From,
Today's production.
That meeting's already done.
I put from a plant, but then be more specific. 50 bottles from a plant. Tell me more about this sample.
It's produced on a random day.
Okay, produced on a random day, if I could fit that in. And there was one more other thing I was going to add in. Who picked the bottles?
Quality control inspectors.
Okay, so I added that too. Selected by. I put QC because I don't have enough room. By QC inspectors. I'm going to put QC because I don't have enough room.
Because you're writing too much.
I am.
Wisconsin.
I'm being very, very direct today. Yes, dear. Yes.
What's that random from the day's production?
At random from the day's production. So it was 50
Yeah, I guess you're
Produce
right.
like the same
random.
amount on every day though.
So maybe I should put 50 random bottles from a plant selected by quality control inspectors. So again, am I being way too specific? Yeah. Do we all get us the 50? Yeah. Okay, statistic. What can I actually calculate?
The average.
That's what I did. 19.6 out of 20. And when I put that in my calculator, I got 0.98. So what does that mean?
Bottles are 98% full.
I mean, I would say 98% of them are. No, hold on.
Yeah, I was gonna say on average, the bottle is 98%, you know.
I was thinking 98% of the bottles were. I think 20%.
That doesn't make sense, 'cause it's
I got
not
20
bottles.
ounces full.
Yeah, that doesn't make sense. It's nothing on a bottle, that's the average
Yeah,
capacity,
we're-
or whatever.
yeah. So 98%, they found that 98%.
I would say they're 98% full.
I was
don't
saying
know.
like each bottle
Is it
is 98% full, yeah.
Okay.
Yeah. That's
I like that. Each bottle is at 98%
I
capacity
think it's on average.
on average.
Yeah.
The 50 bottles are at 98% capacity. I don't think I worded that well, but that's okay.
The ball average
I think that's better. I was just trying to reference back to that sample and not all Arizona tea bottles. Okay, but that is a little disappointing because we're saying most of the bottles actually aren't quite hitting the mark. I mean, 98% is good, and I'm not saying that's bad. It's just I'm paying for this, so I'm expecting 100%. So let's go to the next page. And then, Arizona Tea is going to argue that we have a skewed sample. That we went to the wrong plant on the wrong day at the wrong time. It was a hot day. I don't know. Maybe the bottle split. I don't know what happened. But they're going to argue that we did not do a good sample. So what would we do?
I mean, that could be fair, honestly.
Take
It could
another
be.
one at a different location.
We could take a larger sample, which is one thing we're going to discuss today. But we could also take another sample.
You can go on like every day of the week.
We could keep going and do every day of the week at the same location. But we could take multiple samples.
I thought
And
there was,
so that's what we're going to get to with the sampling distribution.
I thought
Yes,
there was like
sir.
a rule, like the 10% rule. You're supposed to take 10% of the sample.
We're
Or
about
10%
to
population.
We're about to hit that, huh? That was good. Okay, so that was very good. Okay, sampling variability. So, and they let go of the iced tea. I'm the only one on it still for some reason, which clearly you are too. Well,
I mean, you didn't taste it.
I swear. Let me finish the
Oh,
notes
I
where we
think
want
it's
our
like
variability.
shell.
Okay, so if we, Mackenzie, read the first thingy.
Take a sample of 50 adults chosen at random and measure their IQ intelligence.
She's got this.
Then find their average IQ. This is the sample mean. X1.
X1 bar. So it was our first sample. So we put that tiny subscript of 1. Go ahead, keep going, read the next one for me.
Now take another sample of 50 different adults chosen at random and measure their IQ. Then take their average X2 bar. It is very unlikely that the sample means will be equal to each other because we are measuring different.
Okay, perfect. So we did 50 people on the 100 hallway. We did 50 people in the 200 hallway. And it's unlikely that they're going to be equal because we did 50 different people from each hallway. Okay, so this idea illustrates the idea of sampling variability, which we know is important to us. The value of a statistic varies in repeated random samples. We're not surprised. Generally, we use the notion of sampling variability in the following way. So this is Kenzie's suggestion. What if we just took a large number of samples? The larger the sample, the more representative maybe it is of the population, maybe the closer we are to the true mean. Or we could, but notice it's from the same population. So maybe we're doing 50 people from the 100 hallway, then 50 other people from the 100 hallway, and 50 more people from the 100 hallway. Maybe there are some repeats. Maybe we did Shalia with our sample 1, 3, and 5. So we are having some of the same people. We could calculate the statistic, like the sample mean, x bar, or sample proportion, p hat, for each sample. So we could figure out the x1 bar, the x2 bar, the x3 bar, and keep on going until we did, I don't know, 10 samples, so we're at x10 bar. And that's kind of what I was hoping you were going to do with the penny thing, which is fine that you didn't, not a big deal. But if you had, so each group has their own mean, and if we had plotted this, maybe we would have had some sort of a histogram that maybe, and it probably not that beautiful, but maybe it would, if we fit a bell curve to it, maybe it would kind of imply, hey, the mean of this, the mean of all our sampling means, maybe that's close to the true mean of our population. I mean, that would make sense if we did a bunch of samples, and then clearly we're getting closer and closer to the true answer. So if we plot them all on a histogram, hopefully that is the true answer. Okay, so if we were to find lots of samples and make a graph like we did with this little histogram thing, you and I both know anytime we see a bell curve fit to a graph, you and I both know you ought to do what? What is the acronym you should do anytime you see a graph? You ought to cuss. You do. You ought to cuss. So we would examine the center, of course, because we think that center maybe fits our entire population. The shape, the spread, but also outliers. If we had, let's pretend this is the IQ thing, and we had someone really, or a class of 50 that was really low, what could we hypothesize about that class? It's okay. Say what? Okay. So we're assuming they're
Not
Yeah.
the smartest.
okay. So, and again, maybe they are actually pretty smart. Maybe we did a bad job of getting our sample. Maybe all of our other samples are from AP and advanced level classes, and we dared to pull the one regular level class, and they're the ones down here. Maybe they're really not dumb.
I don't think they're dumb.
It just means they're not as intelligent as the other classes sampled. So, did you do did you take good samples of the population? No. Okay, when we make this graph, this little histogram thing that we fit our bell curve to, we get a distribution of a sample statistic, which is called a distribution of sample data. Okay, Ms. Compton gets lazy, and I just start calling a distribution of sample data a sampling distribution. Technically, they are different, but I kind of forget that, blur that line. The sampling distribution of a statistic is the measure of values taken by the statistic in all possible samples. So if I'm not considering all possible samples of the same size from the same population, so if we're thinking about our classroom, for instance, I take a sample from table 1, I take a sample from table 2, I make my histogram. Well, I didn't technically use table 3, so is it technically a sampling distribution? No. Is anyone going to be that nitpicky with you? I doubt it. Okay, and then we wish we would have the population distribution, because that would be all individuals in the population. Maybe that's realistic when we have a small population like our 13, but as for even just the school, who wants to list thousands of points on a histogram to then fit a bell curve? No one does. We're not doing that. So population distribution is not going to happen. But a sampling distribution seems very, very feasible. Okay, so if we're going to describe our sampling distribution, we want it to fit our population well. And so we can apply a statistic used to estimate a parameter back to we're trying to make our sample fit our population. That only works if our statistic is an unbiased estimator. So again, we want to say that the mean on this graph is the mean of our population. That would be our goal. The mean on this graph is the mean of this population. And that's what it's implying down here. The mean of the sampling distribution, that's what I have, a sampling distribution, is the mean of the sampling distribution of sample means is equal to the true population mean. Well, didn't I just plot all the means, put a line in the middle, and say that's the mean of my sampling mean, which I'm trying to say is the true population mean. So seriously, if you understand that graph, you understand this down here. Darn them for having to write it in their fucking new Greek notation, which we've got to just learn to love. And again, to get an actual sampling distribution, you have to take all possible samples of size n from a population. So it's not necessarily always realistic. Now, unbiased estimator, back to if in our graph, in my little fake world of IQs, we had only polled upper level classes, do we think whatever that number is really is the true IQ average for our student population? No. So, duh, we want to have good samples, hence the unbiased estimator. And then Kinsey is right, and this is getting to what Louise wanted earlier. The larger the sample, you would think, the more precise the estimate. Obviously, I mean, I feel like that's redundant. Larger random samples give us more precise estimates than smaller random samples. Well, duh. Who has time for all that, though? The variability of a statistic, or the spread of our sampling distribution, is mainly attributed to the size of the repeated random sample, size of n. Meaning, if we have super spread out versus super close together. Oh, my dot's getting ugly. This is probably dealing with a smaller random sample, whereas that's probably dealing with a larger random sample. The larger the random sample, the less varied our points are going to be, the closer we should be getting to the true mean. And then I was cool with that. I felt like that was intuitive. Maybe deep down in my gut, I knew that to begin with. The only thing I didn't know in my gut to begin with was the line that says, the spread of the sample and distribution does not depend on the size of the population. I thought, like, the school population is bigger than our class population, so it made more sense for a larger spread on school population than on our class population. Now, that's a terrible example because there's such a drastic difference between, like, 2013. But generally, no matter how big the size of the population, the spread of the sampling distribution doesn't have to deal with the population size. As long as, there's always those words. And this is where Louise has learned something. The population size is at least 10 times larger than, flip to the next page, the sample itself. Which is actually named at the bottom. It's called, like, the large counts condition. But we'll get to that in a second. So basically, if we take a sample of size 100, if we have 100 in our sample, how many do we need in our population then? Yeah, we need to have at least 1,000 in our population. So our sample could be up to 100. We could just do 10. But as our sample size increases, the spread of the sampling distribution shrinks, so it becomes much more condensed. So if we did just a sample of 10 from this 1,000, we're going to have a lot of spread. Whereas if we do a sample of 100 from our 1,000, it's not going to have as much spread. As it says, so we don't want to do more because we're wanting this spread to reflect the sampling distribution itself, not anything about our population. And so hence why we're using that 10 rule. So no, don't. Because then you're wondering, like, why is this a spread? Does this have to do with my population itself? You don't want to have to think that. No. Okay, once we discuss the little thingy here, I will Google Arizona TMP. Okay. I think we've talked about this before, but it's always, I like the bullseye. It always helps me. So clearly the center of the bullseye is our goal in life. That's where the true mean is of our population. That's what we're trying to hit when we take samples. We want to know that true mean. Now, if we have bias and variability, those might affect our shots at our target. Okay, bias means our aim is off and we miss the center. Bias can be seen, well, let's go over variability first. Variability describes obviously the scatter, because we've got a lot of different answers. So which two graphs show a lot of variability? They're called A, B, C, and D. Yeah. B and C with such high scatter, they're not good. We want to kind of have minimal variability. Now, A and D look similar. We both have all our points within the same region. Clearly, D is the winner because it's the closest to the bullseye. A shows an example of high bias. So if we're back to my IQ example, what if we only did the advanced classes? Is that actually showing us the true IQ of the school? No. So we've got to be careful with what we discussed in Chapter 5. How did we choose our sample? Is our sample actually representative of the population? Because if we're skewing it, we're not getting near the true mean. Okay, is everyone cool with that? I swear we'll start 7.2 tomorrow and be productive. I've got to know the answer to this question. Now let me stop my YouTube recording. That way Arizona T does not sue us.